Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to talk about Bayes' theorem. Bayes' theorem is a theorem in probability, and in order to understand Bayes' theorem, we have to understand conditional probability. So in my previous video, I talked about conditional probability, so you might need to take a look at that first. But basically, conditional probability says that the probability of event A happening given B, or given B happening, is equal to the probability of A and B, this notation means and, divided by the probability of B. And we looked at various examples of how to use that. Similarly, the probability of B given A will be equal to the probability of B and A divided by the probability of A. So one gives the conditional probability of A given B. This gives the conditional probability of B given A. Often in probability, you will see questions where they ask you for a conditional probability when the other conditional probability is given. And in order to do that, you're going to need Bayes' theorem. So what I'll do is use these two formulas to get Bayes' theorem. First of all, I want to point out that the probability of A and B is going to be the same as the probability of B and A. So let's just change this. From there, I'm going to isolate the probability of A and B by just, in this case, multiplying both sides by the probability of B. So the probability of A given B times the probability of B will equal the probability of A and B. I'm going to do the same thing with this equation. I'm going to isolate the probability of A and B by multiplying both sides by the probability of A. So the probability of B given A times the probability of A will be equal to the probability of A and B. So the probability of A and B is equal to this as well as this, which means that this is equal to this. So let's write those two expressions as equal. We know that the probability of A given B times the probability of B will equal probability of B given A times the probability of A, because each of these is equal to the probability of A and B. Now what I'm going to do is I'm going to isolate this conditional probability, and in order to do that, I'm going to divide both sides by the probability of B. So when I divide this side by it, it's gone, and I divide this side by it, and when I do that, you'll notice that I've isolated one conditional probability and written it in terms of the other conditional probability. This theorem is called Bayes' theorem. A little tip for remembering which probability goes in the numerator and denominator: just follow the same order as you have here. A, and then in the denominator, B. Let's take a look at some examples of how we use this. First example that we'll take a look at is something fairly straightforward. We know the probability of A, we know the probability of B, we know one conditional probability, we want to know the other conditional probability. So let's say these things represent people attending some event. So the probability that Anne will attend the event is 0.55 or 55%. The probability that Betty will attend it is 65% or 0.65. The probability that Betty will attend, given that Anne is attending, is 0.75. So this is the conditional probability that Betty will attend given Anne attending. What we want to know is what's the probability of Anne attending given that Betty is attending. So according to Bayes' theorem, we can find the other conditional probability if we know the one conditional probability and these two individual probabilities, just plugging into this formula. So the probability of A given B will be the probability of B given A, which is 0.75, times the probability of A, which is 0.55, and we divide that by the probability of B, which is 0.65. And when we do the calculation, we get 0.63. So Bayes' theorem allows you to find one conditional probability when you know the other one. But let's look at some more realistic examples of where you're going to use this theorem. This next example is a more challenging question that involves Bayes' theorem, so let's take a look. Each day, Sam's teacher gives the class a warm-up question. 30% of the time, it is a true-false question, and 70% of the time, it is a multiple-choice question. Sam gets 60% of the true-false questions correct and 80% of the multiple-choice questions correct. Today, Sam answered the question correctly. What is the probability that it was a multiple-choice question? So this is a conditional probability question that's asking what's the probability that it was a multiple-choice question given that it was correct. But in order to start this question, let's draw a tree diagram to kind of organize everything, and hopefully you can understand all of these probabilities and how they're all related a little bit better. So we're going to start off with, the question is either true, false, I'll just use a T for true, false, or multiple choice. I'll just use an M for multiple choice. So 30% of the time it's true, false, 70% of the time it's multiple choice. Then, when Sam answers a true, false question, it's either correct or not correct. And we know that it's correct 60% of the time, which means it would be not correct 40% of the time. Similarly, with the multiple choice question, it's either correct or Sam answers it incorrectly. And we know that Sam answers it correctly 80% of the time if it's multiple choice, so that means 20% not correct. Let's now list all the probabilities that we know. We know the probability of the question being a true false is 0.3. We know the probability of the question being a multiple choice is 0.7. We're dealing with the answer being correct, so I just want to deal with this option and this option. So this is the probability of the question being correct given that it's a true-false question. So that's a conditional probability, and we know that that's 0.6. Similarly, what's the probability that it's correct given that it's a multiple choice question? And that's 0.8. Going back to what the question asked, given that the question is answered correctly, what's the probability that it was a multiple choice question? So what we're finding is what's the probability of it being multiple choice given that it was correct? So notice that this is sort of the reverse of this conditional probability. Therefore, we need Bayes' theorem. So let's take a look at completing this question using Bayes' theorem. Here's Bayes' theorem. The probability of it being a multiple choice question given that it was correct will equal the probability of it being correct given it's multiple choice, which we know, times the probability of it being a multiple choice question, which we know, divided by the probability that it will be correct. We don't have that. That's going to take a little bit of work to calculate. There's two ways that it can be correct. It can be correct if it's true and false and answered correctly, or if it's multiple choice and answered correctly. So the probability of it being correct will equal the probability of true and false and correct, or we'll also get it correct if it's multiple choice and Sam answers it correctly. So the probability of multiple choice and correct. I just shifted everything over here so I had room to work. Now, in order to find the probability of true, false question and Sam answering it correctly, that gets into our conditional probability, where it's going to be equal to the probability of correct given that it's true times the probability that it's true. Or means plus. Same thing here. The probability of it being multiple choice and Sam answering correctly will be the probability of it being correct given multiple choice times the probability of multiple choice. If you look at your tree diagram, this probability of true and correct, you're just going to take the product of those two things. So the probability of it being correct, given that it's a true-false question, we know is 0.6. The probability of it being a true-false question is 0.3. So we just multiply those two numbers to get the probability of it being true and Sam answering correctly. Or the probability of it being correct given multiple choice, that's 0.8, times the probability of multiple choice, which is 0.7. So the probability of it being multiple choice and Sam answering correctly is 0.7 times 0.8. We take these two products, we add them, and so now we know the probability of Sam getting a question correct is 0.74. Now we can complete the question. The probability of it being multiple choice, given that Sam got it correct, will be the probability of it being correct given that it's multiple choice, which is 0.8, times the probability of it being multiple choice, which is 0.7, divided by the probability of it being correct, which is 0.74, and we get an answer of 0.7568. So if we know that Sam got the question correct, what's the probability that it was a multiple choice question? 0.7568. So the most difficult part of this question is probably finding the probability of C. But hopefully that tree diagram can help you calculate that probability. Because once you have that, the other things were given, then Bayes' theorem allows you to find that other conditional probability, or the reverse conditional probability. Let's look at this problem, but this time let's find out what's the probability that it was a true-false question given that Sam answered it correctly. So very similar question as to this one. We still have these same probabilities. We have now calculated the probability of Sam getting the question correct is 0.74. And now what we're going to find is what's the probability that if Sam got the question correct, what's the probability that it was a true-false question? We know the reverse of that, the probability that Sam gets it correct given that it's true-false. But now we want to know what's the probability that it was true-false given that Sam got it correct. So again, we're going to use Bayes' theorem. The probability that it's true-false given that it's correct will be equal to the probability that it was correct given that it was true-false, so the reverse. Then we multiply by the probability of it being a true-false question divided by the probability of it being correct. So very similar to what we just did. We know all of these values now, so we plug in. So the probability of correct given that it was true-false is 0.6. The probability of true-false is 0.3. Divided the probability that it was correct. When we do this calculation, we get 0.2432. And if you compare it to our last example, this value is equal to 1 minus that other conditional probability, which makes sense because both probabilities should add up to a 1. I hope this example helps you understand Bayes' theorem. There's a lot going on in this question. Use a tree diagram, list your individual probabilities, calculate any probabilities that you need, and then plug in so that you can find this conditional probability when you know the reverse conditional probability.